So this week the only assignment due is the Chapter 3A questions and then the discussion on Chapter 3A. So I might start Chapter 3B on Friday, otherwise I'll save the whole thing for next week. But I think we'll finish the 3A stuff today. So we ended last class by, let me switch yours here. We ended last class talking about binary ionic. So we looked at the main group metals only, the alkaline earth metals, and how they were mixed with the nonmetals. And we named those, we came up with chemical formulas for them. So now we're going to go add on another layer. So we're looking at polyatomics next. So for polyatomics, what these are is they're two or more covalently bonded, I shouldn't say ions, atoms with a charge. Okay? So if you notice, you'd have to look at this polyatomic table in order to name these. So the polyatomic table is located on the same handout that has the electronegativity tables on it, which we used last class. So notice that all of these polyatomics, we just said two or more covalently bonded atoms. So almost all of the elements present in these polyatomics are nonmetals. I said almost all, because there's always exceptions, right? So they're covalently bound to each other, but overall they have a charge. So since they have a charge, since they are known as ions, because electrons have been transferred, okay? So we're going to use this polyatomic table to name these ionic compounds. So the best way is to just do it. So that's why I just put up the chemical formulas. That's what these are. So we're going to explore, first off, how do you know there's a polyatomic in it, and then how do you name it. So this first example, we have barium, sulfur, and oxygen. So I have 3 elements present. We haven't named any with 3 present. We've only named with 2. So once you see that there's 3 elements present, that should give you the hint that, hey, one of these is probably a polyatomic. Okay? And notice most of the polyatomics have a negative charge. So most of the time, your polyatomic is going to be the anion, the negatively charged second portion. Okay? Not always, but most of the time. So since there's 3 elements present, how would you name that, right? Barium, sulfur, oxide? No. That means there's a polyatomic in there. So you would look and try to see if you can find which one it is. So when we name these, they're still ionic compounds, so we're not using prefixes. Okay, so we'll start by naming the metal portion first, which in this case is Ba, barium. And now, this SO4, that's a polyatomic part. So we would look up SO4 on the table and write whatever the name is on that table. Sulfate. So no IDE endings added to it, just write it exactly how it is in the table. So looking at the next one, once again, how do you know if it's a polyatomic? Look how many elements are present. There's 3 again, lithium, chlorine, oxygen. So that means there's probably a polyatomic, most likely the second half of the chemical equation. So the polyatomic in this case is going to be your ClO3. So to name it, name the metal first. Lithium, and it's chlorite. ITE? No. ATE? ATE? See, this is the hard thing about these two. If you notice, the polyatomic table, they differ just by a letter. So like ClO3 is chlorate, but ClO2 is chlorite with an I. So pay close attention to your spelling when you're doing polyatomics, because just changing one letter, you're talking about different polyatomics. Right. That's what the polyatomics on the bottom. Now this last one. So once again, 3 elements present, nitrogen, hydrogen, and chlorine. Now we said usually it's the second half that's going to be the polyatomic, but not always. So I had to write the exception up here, right? So Cl, that's just chlorine by itself. That's an element. So the first half in this case is the polyatomic. So NH4, what is that? Ammonium. So the reason it's first is because that's the only polyatomic on the table that has a plus charge. And we always name the cation portion first. And then chlorine becomes, so we're back to the rules for a binary. We add the IDE ending. Chlorine will become chloride. Now, write some names and we're going to go the other direction. Sorry, I was looking in the wrong spot, the wrong names. So, do that one. I'll write that up. I'm going to be weird, I'm going to start here and go that way. So aluminum sulfate, so this is ATE. So looking at it, how do you know there's a polyatomic? What's really going to help most of the time is that ending. Okay, if it's not a polyatomic, so if this was sulfur from the periodic table, it would have an IDE ending. Okay, but since it's ATE, that's a hint, okay, it's a polyatomic. All right, so you know I need to look at my table to figure out my ion. All right, now there are a few polyatomics that do have IDE, so keep that in mind. We have cyanide has an IDE and hydroxide. But all the other ones don't, so those are the two exceptions. So how do we write the chemical formula? We're going to do it the same way we did binary ionic. We're going to write the symbols with the charges. Okay? So the symbol for aluminum, we look at our periodic table. And we need the charge.
SO4.
Plus 3. And so SO4 is the sulfate. And what's the charge on the sulfate?
-2.
-2. Okay, so the plus 3 on aluminum, we know that because it's in group 13, it loses 3 electrons to become a plus 3. The sulfate ion, we just found that on the table and it told us the charge. Okay. So now, there's 2 ways that we did this last time. One was the crisscross method, where you take the number, not the charge, and it becomes the subscript on the opposite ion. So doing it this way, it tells me that I should have 2 aluminums and 3 SO4s. Okay, the other way that we did it was to balance out the charges by adding ions to both sides. Kind of did a quick way here, but you would have to go back and forth until you got the same charge on both sides. So what I mean by that is a plus 3 and a plus 3 on the cation side give me a plus 6. If I had 3 sulfates, each with a -2 charge, I would have a total of -6. So those charges cancel, and it's an overall neutral compound. Both ways give you the same answer, right? Because we just said 2 aluminums, yes, there's 2. Al2, and then 3, so this 3 goes here for 3 sulfates, and there is 3 sulfates. Now, when you write that there's 3, don't do this. Because what that does is it tells me I have 43 oxygens and 1 sulfur. Okay? So what we need to do, if there's more than one of a polyatomic, put parentheses around it. That way you're saying there's 3 SO4s. So there'd be 3 sulfurs and 12 oxygens. So if there's only one polyatomic, one of those ions, you don't need parentheses. If there's more than one, put parentheses. All right, should we try potassium nitrate? So potassium, we need the symbol, the alkali metal. It's actually K, so that's why it's kind of hard to find that one. So it's number 19. It's the atomic number, and what's its charge going to be since it's an alkali metal? Plus one. Everyone in group 1 has a +1 charge all the time. NO3 is the nitrate. It just says minus, so that would be a -1. Awesome. Okay, so now you can do the crisscross method, or you might even just notice, hey, the charges cancel, right? So since they cancel as is, that means you just need one of each, so you would just write KNO3. And I didn't need to put parentheses this time because there's only one NO3. All right. So I do this next one in trick S. So notice the endings, strontium nitride. Is this a polyatomic? It's got an IDE ending.
No.
Are there? So no. So that's why I wanted to throw this one in there, because they're not going to tell you, name this polyatomic ionic compound. They're just going to say, name this ionic compound. So you need to be able to tell if there's a polyatomic or not by reading it. So this IDE ending, it's not cyanide and it's not hydroxide. Those are our only two IDE endings for polyatomics. So that means it's an element from the table. So start by writing strontium first. So what is the symbol for strontium? It is an alkaline earth. SR, what's its charge?
+2.
+2, because it's in group 2, so it's going to lose 2 valence electrons. Now nitride, that's the IDE version of nitrogen. So find nitrogen on the periodic table, just N, and so its charge is in group 15, -3. It's going to gain 3 electrons to have a full octet, become noble gas state. So now you can do crisscross or write your list of ions, whichever method you prefer. So this would say I need 3 strontiums and 2 nitrogens. So that would be the correct chemical formula. Questions so far? You want to try a few more before we do transition? All right. It's dangerous because I gotta make them up. Just, you never know. Good marker, my bad marker, actually. Three more, let me look at transitions. What do I got? I don't know if this is a possible compound, but we're going to write it anyway. All right, let's try these guys. We'll start with the hardest one. Ammonium acetate.
NH4+.
Okay, so you noticed right away ammonium's not an element on the periodic table, it's actually polyatomic. Okay, so what about acetate? Is that a polyatomic or an element?
It's
Polyatomic. Just -1? Oh, so it wasn't that hard because of the charges anyway. So I wanted to show this one because you can have an ionic compound with 2 polyatomics together. It doesn't have to be a metal with a polyatomic. Okay, because notice these are all nonmetals, but it's still an ionic compound. So that happens sometimes. The reason it's ionic is because ions are involved, charges. So we need just one of each. So you just put them together without the charges involved. So that would be the correct chemical formula. All right, let's look at lithium chromate. So lithium, alkali metal, in group 1. Plus 1, so it's Li plus 1. And then chromate, that ATE tells me it's a polyatomic.
CRO
2 minus? Is that right? Okay. So do they balance how it is, or do we need to add more of one? Add more. So we add another lithium. Same as the crisscross method. I just show both ways because I never know what people prefer. So this would give a +2 and a -2 on that side, so it's neutral. So we need 2 lithiums, so Li2, and then CrO4, just one of them. All right, last but not least, barium cyanide. So barium, Ba, what's its charge?
Barium is
+2, it's an alkaline earth metal, it's way at the bottom there of group 2. Cyanide,
And CN minus 1.
Cn-1. So the key here is it has an ID ending, but it's not an element on the periodic table. You're not going to find cyan somewhere on there. Okay, so now you just need to do the crisscross or add another anion, so another cyanide. And that would give you Ba, just one of those, and then 2. Is that correct? There's something wrong with it. What's wrong with it? I'm saying there's 1 carbon and 2 nitrogens. Oh, you got it, I need my parentheses. Because I want 2 CNs. I need 2 carbons and 2 nitrogens. So by putting my parentheses in the 2, I'm saying there's 2 carbons and 2 nitrogens. Without the parentheses, there was only 1 carbon. Pay close attention. That's the most common mistake I see with polyatomics, is people not putting the parentheses, and then it is wrong. So. Now we're going to add transition metals into the gold. And we'll just do a whole bunch of examples with a hodgepodge of everything. Transition metals. So far, when we've talked about metals, notice they've all been either alkali metals or alkaline earth metals. They've been the main group, the representative metals. With them, we know what charge they are based off of where they are on the periodic table. But now we're going to talk about the transition metals. That's the D block, those center metals. Okay? We don't know what their charges are based off of where they are because they have variable charges. So what that means is they can have more than 1 charge. It just depends upon what they're attached to, what they're with. So it's our job to figure out which ion is present in that particular element, in that particular compound. So to determine the charge, we are going to look at what it's bonded with. Okay, so what I mean by variable charges, if I didn't explain that well, for instance, copper can have a 2+ charge, or it can have a +1 charge. So we need to figure out, okay, given this compound, given this chemical formula, which one are we talking about? Is it copper 1 or is it copper 2? Okay, so we're going to start by naming, because that's how we've done it so far, is we've had the chemical formulas, turned it into names. So we'll start there and then do the other. So let's do UO, 2O, and Fe2. Might as well bring in the polyatomic right after that. Right. So, when you're looking at these, we know they're ionic because it's a metal and a non-metal. Okay? But now that we have transition metals, when we name them, Since it could be the +2 copper or the +1 copper, we need a way to signify that. So how we do that is by putting a Roman numeral after the metal's name. So we would put Roman numeral 1 if it was the copper +1 ion. We would put a Roman numeral 2 if it was the copper 2+ ion. So it's our job to figure out which one it is. How do we do that? We're going to look at what it's attached to. I don't know what copper this is. I don't know the charge on it. But I do know the charge on oxygen. I can figure that out based off of where he is on the periodic table. So looking at where he's at, he is in group 16. So he's going to have a -2 charge. And I said that these compounds are all neutral, right? They don't have a charge outside of them. So if they're all neutral, what does my charge on the copper have to be to cancel out this -2 charge? Positive 2. So based off of what it's attached to, I just figured out that the copper in this compound is the copper +2 ion. So we're using what's attached to figure it out. So to name it now that I know what its charge is, I can name it. I just take the metal name, no prefixes because we're still talking ionic. It's going to be copper. Since it's a transition metal though, I need to indicate this charge, and I do that by doing Roman numeral 2 because it's the copper +2 ion. You only use Roman numerals for transition metals, don't use them for the main group metals. Then the second portion, oxygen, we name it just like we did the binary ionic. Oxygen becomes oxide, we add that IDE ending. Right, I'm going to erase this to give me more room to show this one, because this one gets a little more complicated. So now we have another copper oxygen compound, but the formula is different. So that means the ion's probably different. So to figure it out, so this 2 here is saying there's 2 coppers, right? So I'm just going to draw that out. We have copper here, copper here. Do I know the charge? Not yet. So I'm going to put a question mark by its charge. But we have just 1 oxygen. Okay. What's the charge on oxygen? We just said -2. So that means on my anion side, since I have just 1 oxygen, I have a total charge of -2. So these are going to be +1, right? You need a total of a +2 charge over here to cancel out that -2 charge. But now since you have 2 coppers, you need to distribute that charge evenly across both. Okay, so since there's 2, divide it by 2 and you get +1, +1. So this is the copper 1 ion. So when I name it, the name's very similar. The only thing that differs is the fact that I have a Roman numeral 1 instead of the 2. Oxygen is still going to become oxide. Now let's name one with a polyatomic in it. So the same rules are applying. We don't know the charge of the iron, but we do know the charge of the polyatomic. We can find that on the periodic table. So I'm going to start by writing out, I'm going to use a different color, all my ions. So I have 2 irons, so I'm going to write iron, don't know the charge, another iron, don't know the charge. For the sulfates, I shouldn't have drawn that line because there's 3 of them. We have SO4, SO4, and an SO4. What is the charge on that sulfate ion? So you're looking at the polyatomic table. -2. So that means each of these 3, because there's 3 of them, because there's a 3 on the outside of those parentheses, each of them has a -2 for a total.
-6.
So what do I need on the cation side? +6. Once again, I have 2 irons, so I need to take that charge, divide it by 2, so that I evenly distribute on each of those irons. 3. So +3. So all this work just to figure out what my Roman numeral is. Okay, so it's going to be iron with Roman numeral 3. And you don't have to put parentheses. I sometimes do and sometimes don't. Sorry for the both ways of it. And then SO4, I already said what it is, but to figure out that, you would look at your polyatomic tables, and it is indeed sulfate. So let's try to go the other direction, where we take the name and come up with the chemical formula. And then with the time left, we'll just do more examples of all this. So manganese. So we'll try these three. So these are the names. We're going to come up with the chemical formula. So you can identify these as transition metals just for the fact that they're using Roman numerals. So we're going to approach it the same way we did with binary ionic and the polyatomics that we looked at. So we're going to take the symbol with the charge. So manganese, we're looking in the D block to find that guy. I think he's number 25. So his symbol is Mn. And since we don't know the charge based off of where it is, we have to use the Roman numeral to write the charge. So Roman numeral 4. So this is going to be a +4. I know it's a plus because the metal portion is positive. Metal portions are cations. And because it's first. The first element named is the cationic one, positive one. Now oxide is what? Just oxygen. We've used him quite a lot, so you might even memorize his charge by now. It's -2. He's in group 16. He needs 2 valence electrons for that outer shell. Okay, now, it's what? Go ahead. We need 2 oxygens, right. So you need to add another oxygen because the charges didn't cancel. So we have a total of -4 +4. I'm glad you did it this way, because let's see what happens when we do the crisscross. Yeah, this way makes more sense usually if you're trying to visualize it, because you can say, okay, I need 2 of those with 1 of those. So this would give me the chemical formula Mn, just 1, and then 2 oxygens. This is correct. If you did the crisscross method, notice what you're going to get is Mn2, and then O with the 4. Okay, this is not the correct formula. So if you do crisscross, you always need to double check and see, can I reduce that down further? Because in this case, you can reduce it further. If you divide the common denominator both by 2, you would eventually get Mn1 and then O2. So you could come up with the same thing, but you need to notice. So if that's the way you choose, crisscross method's what you want to do, just make sure you're double checking your answers. The long way gives you the right answer every time. So, all right. So silver 1 nitride. So silver, looking at the transition metals. You know, it's a symbol that doesn't make sense with the name. Ag. It is Ag. What's its charge? +1. We're looking at the Roman numeral to figure that out. And then nitride is just nitrogen, so N. -3, yes. So, crisscross method, or you can look at it like, I need more positives. How many more? 2. That way, +3 canceling out my -3. So I have 3 silvers, 1 nitrogen. Ag, 3, N. cobalt 2 perchlorate. Cobalt, transition metal, what's its symbol? CO, what's its charge? +2, so that's what that Roman numeral 2 is telling us. It's the +2 ion. Perchlorate, is that an element or a polyatomic?
No, polyatomic.
The ATE tells you it's polyatomic. CO04 negative. So pay close attention, because isn't this the one where if there's an I there, it's Cl03, it's chlorite. So yeah, pay close attention to the letters. And it's just a -1? Okay. So doesn't even out. We need another perchlorate ion. Now it's good. So we have 1 cobalt and 2 perchlorates. Cl4, 2. Is that correct?
No, you
No.
need the parentheses.
I need the parentheses. It looks like I have 42 oxygens over there. We don't want 42 oxygens. So let's do the parentheses with the 2 outside of the parentheses. Right. That's the end of the chapter, but we've had a lot of time left, so you just want to do more examples with transition metals? Is that kind of where we're at? Okay. So, I just read a part, but saying that work. So, it's always there. Ooh, that one. Right. We'll start with those two. And then we'll do some names getting into chemical formulas. But with the transition metals, I feel like naming them from the chemical formulas is almost harder because you have to figure out what the charge is going to be. So to do that, remember, we're looking at what it's attached to. So how do I know if it's a transition metal? You find the symbol, you see it's in the D block, so you know that you don't know the charge and you're going to have to figure that out. To figure it out, we look at what it's bonded with. So we don't know palladium, that's what PD is, question mark, but we do know chlorine. -1, it's halogen. All halogens are -1. But how many chlorines do we have? This number here
2.
shows us. We have 2. So we need to include both because we need to figure out the total charge. So the total charge is -2. So that means palladium has to be +2 because there's only one of them. So that entire +2 to cancel out that -2 has to go on that one atom. Now, for those of you who like the crisscross method, you can think of it as reverse crisscross. So this 2 is the charge on palladium, and this 1 is the charge on chlorine. Chlorine -1, palladium +2. Just like when we do the crisscross method, this is not 100% foolproof every time. Okay, so you might want to write it out this way, and you'll see that in this example. But now that we know the charge, let's name it. So we're not done. The whole reason we figured out the charge is so that we could know what Roman numeral to put in the name. So PD is palladium. What's going to go after that? Roman numeral 2, indicating the charge since it's a transition metal. And then chlorine becomes chloride, right? We're doing ionic, so we're not using prefixes. So this is the correct name, palladium 2 chloride. So the next chemical formula, MnS. Mn, number 25, manganese. So let me start by writing my symbols again and the charges. So I don't know the charge on him because it's a transition metal, it's in the D block, number 25. But I do know sulfur, I can figure it out based off where he is. -2, because he's in group 16 along with oxygen, so they're going to both be -2 charges when you form ions. I have just one sulfur and just one manganese, so what does the charge on manganese have to be? +2. I need to cancel out that -2 charge, so that means this has to be a +2. So that's going to be the Roman numeral that I put after the name. I might be spelling that wrong. What goes after manganese? Roman numeral 2, and then sulfur becomes sulfide. Yes. Let's do one more like this, and then I'll do some naming in reverse. Just trying to figure out an example here. Oh. It's a weird looking one. Let's name him. W stands for Wolfram, but it's Swedish name, so we don't use the word Wolfram in English. So if you find W on the periodic table, it's number 74. It's tungsten. Yep, tungsten is its actual name, so that's why this one's a tricky one. The W is tungsten. But before we can name it, we need to know the charges. Okay, so tungsten we don't know. How many tungstens are there? If there's no number, you just assume it's a 1. Okay, so there's just one tungsten. Now notice we have parentheses, so what does that tell me about what's inside the parentheses? There's 2 of them. It's a polyatomic though. Okay, so that means I'm going to keep it together. So OH total, what is the charge on OH total? So I'm going to look in the polyatomic table to figure that out. It's hydroxide, but the charge on it's -1. That's what we're trying to figure out. What is the charge on tungsten? How many OHs do I have? You just said 2 a second ago. That's what this 2 means on the outside. So I'm going to write 2 of those. Each have a -1 charge for a total of -2. So that means I need a +2 over here. Since there's only one tungsten, the whole charge is going to go on that. Yeah. So now let's name it. Tungsten, and Roman numeral 2. I'm picking a lot of +2 ions. So what happens when I go? And then OH was what? Hydroxide. So do you want to do more chemical formulas to names, or do you want to do the other direction now?
Can we do one with if it was negative? Like would it ever, no, it would never be negative because it's first, right?
The metal, yes, the metal's always going to be positive. We can do one where there's more than one. Have it in more of those in a little bit here. So let me get my polyatomic table because that's going to help. CR3PO4. All right, so there's more than one element present. So even though you don't see parentheses, you should recognize that there's a polyatomic somewhere in here. So we want to figure out the charges. So I like to do that by writing how many ions of each in a list and seeing their charges. So there's 3, this 3 says there's 3 chromiums. So I would write Cr, Cr, Cr. Since it's a transition metal, I don't know its charge. I'm going to look at what it's bonded with to figure out its charge. And it's bonded with this polyatomic, PO4. There's only one of them. Okay? So PO4, I look at the polyatomic table and figure out what is the charge on PO4. -3. So since there's only one of them, my total charge on the negative side is a -3. So that means to cancel out that -3 on the cation side, I need a +3. But there's 3 atoms, so 1 each, right? So you just divide by how many atoms. And in this case, there's 3, so 3 divided by 3 gives me 1, telling me that each of these chromiums is a +1. Now that I know the charge, that's my Roman numeral when I write the name. So, chromium. Roman numeral 1. And then what's PO4? What's the name of that? So you look at the polyatomic table to figure that out, and it's phosphate, AT ending. Time for one more. So let's try taking a name now and putting it in a chemical form. So copper, you would have to look up the symbol. I know it's a transition metal because the name has a Roman numeral in it. So that's my clue that it's a transition metal. And to look for copper, I'd look in the D block. So copper's Cu. What's the charge on copper? +2, so we're looking at the Roman numeral to figure out the charge. So that Roman numeral 2 tells me copper has a +2 charge. That's why we write it there, otherwise we have no idea. And then phosphide, so is that a polyatomic or is it an element? It's an element. It has an IDE ending. It's not cyanide, it's not hydroxide. Those are our 2 polyatomics with the IDE endings. So we know that it's actually an element from the periodic table. What element? Phosphorus. Right underneath nitrogen, we have that P, phosphorus. So what is the charge on phosphorus? -3, just like nitrogen. They're in the same group, so they have the same charge, the same oxidation number. So now, you can do the crisscross method, or you can just keep adding to both sides until it's neutral. Okay, so there's more negative. I'd have to add another copper. Now I have a +4 here and a -3 here, so I'd have to add another phosphorus. Now there's too many negatives, so if you just kind of go back and forth until it finally evens out. Okay, with the odd numbered ones where you have 1 even and 1 odd, it's really a lot simpler just to do the crisscross method. And since one's an even and one's an odd, you know you're not going to have to reduce it down later. But either way works. So 3 coppers. So Cu3, and how many phosphorus? 2. Yep, so the 2 goes there, or you can just write it out and count them. So this would be the correct chemical formula for that guy. And I think I'm making up compounds now because I'm pretty sure that's not a compound that's actually ever been made. But we can name it with our system, so. All right, so Sundays when the homework assignments are due. On Friday, I will still be here going over stuff. If anybody comes in person and has questions, that's what I'll do. If nobody comes, I'm going to start chapter 3B, just so that you have enough time to get all that information in. So.